So we do want to label some key points on here and some key stuff. So just, you should at least clearly have marked in your graph that it has a maximum. It goes up to +1 and a minimum down here at -1. You'll have to be specific about those kind of details. And if you can't see quite where these points are, it's 0, then pi/2. The next one here is pi. Then this would be 3 pi/2 and 2 pi. Okay. So we're going to do the same thing for the cosine, and it's going to happen at the same points. So cosine's a little different. It starts here this time up at 1. And this is the graph you're going to get to know really well for cosine. And I'll do the pattern on going the other direction as well, so I'm going to go this way. But you need to have a very nice picture of cosine. As I said, everything we do will start here and transform it. So the reason that you guys are forced to go through these trig graphs as well is that they're called periodic graphs. And for a lot of things in nature, they follow this pattern. So can you guys think of anything that repeats in nature? Yeah. Radio waves, yeah, frequency, that kind of stuff. So when you turn into, like, I guess this will be a shameless plug, 99.3 the Fox, or, Virgin Mobile 95.3, or whatever you listen to, those are frequencies that the radio station's playing at. That's what FM is, frequency modulation. So yeah, there's a bunch of trig stuff in there that they have to do for your car stereo to figure out those sounds and play them through the speakers. But like just stuff that repeats. Like I'll give you an example here. The seasons, right? We live in the northern hemisphere, and summer comes every June, July, August, and winter comes every January, February, March. Every year it repeats. You can even look it up on Google and find out, what's the average temperature supposed to be, I don't know, on this day in next year on August 10th, right? Because those patterns keep reproducing, so we can make pretty good guesses about it. But what else? What else just repeats? Yeah. The day. Yeah, every day, right? The Earth makes one turn. We see the sun one time. We can predict when the sun's going to rise, when the sun's going to set, how much daylight we have, all those types of things. So yeah, that's you're going to see lots of applications in this unit. The tides is another example. High tide, low tide. Pretty much everything that's repeating on a continuous fashion is going to have that. So the period of these graphs is how often it repeats. And I'll show you here, I'll use a thick marker. So something like this. So between those black lines, there's one sine graph, one cycle of it. Everything else is a repetition of this black box that I've just enclosed, right? Same thing with cosine. If you box it off like this, that makes up one cycle of the cosine graph. So to know how long the period is, here in this case, it's the length it takes to do that. It's 2 pi. So it goes all the way out to 2 pi for both graphs. So sine and cosine, they repeat themselves every 2 pi. Okay, so the other sort of things we need to work on, there's a center line in these graphs, and it's also known as vertical displacement. It'll make more sense when we do transformations, why it gets that name. But the center line, can anybody, if you look at these graphs, do you see what a center line might be drawn on them? It might be better to call it a middle line. Yeah, Daniel. What? So are we talking vertical, horizontal? So let's see here.
Or sorry, pi -1.
Pi there?
Like that.
Oh, I see. Yeah, okay, that makes sense. That is right in the middle of the sine graph. If we look at it, I'm not being specific enough here. That cuts it right in the middle, which is correct. But what I should have said is, if you look at this graph and you want to draw a horizontal line, right? Draw a horizontal line through it. Can you see where the middle would be on a horizontal line? Yeah, it's at 0. So I could draw a horizontal line like this. And what that does is half of the graph is above and the other half is below. Right? So that's what we call the center line here. And that happens at y equals 0 for both of those graphs. And then the amplitude. What's the amplitude? Does anybody know what that is on a trig graph? Any physics people done that yet? Yeah, so the amplitude describes how much this graph moves away from the center line. So that's what I've drawn in purple here, is the amplitude. Okay. So the distance that the graph moves from center. And in both cases, it's 1. Now, one thing to be careful of, we're using distance like a scalar, meaning there's no positive there's no negatives here. It's just a positive value. So we always talk about, like, this isn't an amplitude of -1 because it dropped. This is the distance it went away from the center line, and that distance is 1. So we would always say the positive number for amplitudes. Okay, and we talked about this one earlier, that the maximum happens at y equals 1, and the minimum happens at y equals -1. So we could write that like this to show you what the range of the graph is going to be. So we'll get lots of practice working on these properties, but this is our starting point. You have to know how to do these graphs, and these key features of it are something that we're going to bring up just about every time we do a graph. So hopefully it starts to sink in a bit by the end of our block, if not right now. Oh, sorry, one last thing. This is a real handy technique. This is my favorite way of dealing with the graphs, is to split it in 4 equal sections. So I've already messed up our sine graph a lot, but I left the cosine one without being written on. So what I want to show you is, I'll show you 4 equal pieces. Here's 1, 2, 3, 4. So 1, 2, 3, and 4. Now the reason it's handy to think about the graph in 4 equal pieces is those mark all the key points. For example, the first key point is right here at the beginning. The next key point is right here. It lines up perfectly to the edges of these 4 equal intervals. So when you're trying to draw the graph, that's always my starting point, is where are my 4 equal intervals, so that I know I start at the top, then I go to the center, then I go to the minimum, then I go to the center, then I go to the maximum. So I can follow the pattern once I know how far apart they're spaced. Okay, so I'm going to take all that off the screen. Cover up your book if you've already written those graphs down. Test yourself, see if you can reproduce those too. Okay, so the sine graph starts at the middle, then it goes up to the top, then to the middle, to the bottom, and back to the middle. So that's how the wave goes through for sine. Middle, top, middle, bottom, middle, top, middle, bottom, middle, top. It just keeps going through like that. The cosine follows the same pattern, only it doesn't start at the middle like this one. It starts at the top. So it's going to go top, then it's going to go middle, then bottom, middle, top, middle, bottom, top, middle, bottom. It just keeps going through the same pattern. So that's what my cosine graph would look. That's a terrible cosine graph, but it kind of looks like that. Okay, and this whole length, just to give you one more reminder about it, is 2 pi. And every equal quarter, I hit my key points. Does So that's how I know where the top, middle, bottoms all happen, is they all happen right at those equal quarters. All right. So we're going to do some basic transformations today to get started. Test yourself again. What would this do differently? Can somebody explain it in terms of trig? What does putting a 2 in front do? There's a new word you should have learned today. Sure, S. Yeah, the amplitude is going to change here. So this time, it's going to move twice as far from the center line. It's going to be 2 up and 2 down. Okay, so try those two graphs, see how you do with them. Okay, so again, you're just getting used to the pattern now, but hopefully it's sinking in. You're going to start at the center, and you're going to go up. This time, here's 2 pi. So here's my quarters. So that's going to be the maximum. Back to the center, down to the minimum, back to the center. So it should look like this, going up as high as 2, going down as low as -2, about like that. And in the next graph, it starts at its maximum. The maximum is normally 1, but it's been tripled, so its maximum is going to go all the way up to 3. Equal quarters again. Here's where I'm going to find all the rest of the points. So I'm going to move down to the middle, then down to the bottom. Here's where it'll bounce back up to the middle, then back up to the maximum. So the cosine graph would look like that. Now my cosines are off today, I guess. Okay, so in this case, again, just to remind you that the amplitude should be the absolute value of what you see there. If I was to give you a problem that said, like, what's -5 cosine of x, and ask you what its amplitude is, the amplitude in this case, we would still call it 5. Okay, so it's always going to be the absolute value of whatever letter is in front there. So, like those two guys. That's a favorite multiple choice one, by the way. It's like your choices would be 5, or another choice would be -5, right? They're trying to mix you up, but it's always positive. We just want to know how far away it is from center. There's another way that you can get the amplitude, which is a little more clever, and it's helpful to us when we change problems around on you a bit. And that's to think about it as the middle, right? Or sorry, as the distance from the middle. So if I know what the maximum is, in this case it's a 2, and I know what the minimum is, it's a -2. How far did I have to move to get from there to there? 4 units, right? But that's all the way from the top, all the way to the bottom. The amplitude stops in the middle, right? So the amplitude is going to be half of that. Same thing, if I was to look at the distance here, this time the distance from top to bottom is 6. That means if I didn't see the equation, I should know that the amplitude is half of that, because it stops at the middle. So it's going to be the maximum minus the minimum. That's the distance between the two, divided by 2. Sometimes you're going to see a problem that maybe doesn't give you an equation. It gives you some information about the trig graph, and it's one handy way. We'll talk about it more again later. It'll come up, but it's probably one of the more useful ways of thinking of amplitude as well. So that's vertical stretching. We call it the amplitude. The next thing we're going to do is we're going to mess around with horizontal stretch factor. So if you're wondering why are different names for the same things we already did in transformations, is because these things have so many applications that physicists went and did more work with them before math did. So by the time they were done, they had all these names for stuff like a phase shift, which is coming up. And you may go, well, what's a phase shift? Well, it's a horizontal stretch. It's just again, it's just a term that came up because they beat us to it, I guess. So this phase shift for a horizontal stretch factor is going to affect the period. Because if you picture this graph getting narrower, I'm going to change the length that it takes to make one cycle of it. Right? I'm going to either make it longer or shorter. So we're going to take a look. Oops, sorry. We're going to take a look at these on a graphing calculator. So grab your graphing calculators if you don't have them. Okay, so this one's a little nicer to see than the little Trig one. So I'm just going to use, than the little TI one. So I'm just going to change this slightly. And I'll go from negative 2 pi to 2 pi. You could do that on your negative 2 pi to 2 pi. You could do that in your window. This is the same as the window settings on a TI-83. And negative 2 to 2, I guess. So this time I'm going to take a look at the sine of 2x. Yeah. So if you look at this graph, how many, let's see, how far, there's one cycle. Can you guys see the crosshairs okay from where you're sitting? So from here, there's the start of my sine graph, right? And it's going to keep going like this. And there's where that cycle ends. You guys see how far that is this time? How far was that? It was pi, yeah. It was half what it was before. It's now pi. So the period for this graph is pi. Okay, so we'll take a look at sine for if we put 4x in this time. It's even more sine graphs now. So we'll try it one more time here. If I start, here's where the cycle begins, right? And then it ends right there, because otherwise it's going to repeat. So how far did I move along the x-axis to get here? Yeah, it's pi over 2. So this time there's a period of pi over 2. Okay, so I'm going to change up my range here just to make sure this will fit. So let's look at the sine of 1/3 of x. See if I can get a better axis there. There. Okay, so can you see what's the length of that period this time? It's 6 pi, yeah. So putting that 1/3 in there, now I have 6 pi. And the last one, maybe you can see the pattern. Maybe you're already deathly bored, but let's look at one more. Make a prediction. What do you think is going to happen when I put in a half? What do you think the period of the graph is going to be this time? 4 pi. I did hear a couple people say that out there. So how is it working like this? Well, we start with 2 pi. And in this case, my horizontal stretch factor is 1/2. So half of the original period. Here, it's going to be 1/4, right? Here, the horizontal stretch factor is 3, which is, you get this from going 3 times 2 pi, right? So that's all we're doing is we're just using the horizontal stretch factor to make the period bigger or smaller. And then this one, of course, horizontal stretch factor is 2. 4 pi is the same as 2 times 2 pi. So you can use your transformations knowledge to answer these questions, right? You apply that horizontal stretch factor to the period, you'll find out what the new one is. Because we're going to be using these graphs so much, we're going to talk just about techniques for trig because we literally are only going to transform these trig graphs. We want to be efficient at them. So when you run across this sort of thing like sine of bx or cosine bx, this is the period. It would be 2 pi over b. Okay. Now, the other thing to keep in mind here is that your textbook is for grade 12s, although we're a calculus-oriented class. We'll focus mostly on radians because we're headed to calculus right away. But your textbook may ask you for it in degrees. It just means you're dealing with 360 degrees divided by whatever that number is. Okay. Okay, so see if you can make the transformation now. We already did amplitude. We changed the amplitude and you guys drew it. See if you can change the period of the graph now and draw this. You can use the scales I've set up for you there. I've already set them up on the graph if you're drawing your own. So I'll just make sure you're on the right track. If you're kind of puzzled at how it goes, everything is the same. Okay, everything is the same. The only thing we've done now is we've compressed the graph in. So normally I'd have a period of 2 pi, but now I'm going to have 2 pi over 4 or pi over 2. So that means it stops right here. That's the full sine graph, right? If it stops there, where am I going to find my key points? They're still going to be every quarter. So here's my equal quarters. That's where I'll find them. So cosine starts at the top, goes to the middle, then to the bottom, then the middle, then the top. So here's what it would look like for one cycle of the cosine graph. And it's always good practice just to get the flow of this and remember how it works. Here would be another cycle. But that's what if you use the same scale as me, that's what you should have for your graph. Okay, your key points here are going to be every pi over 2 is the whole thing, and we're going to divide it by 4. So that's pi over 8, which in this graph is every tick mark. Okay. Hands up, how many people are able to do that? Okay, good. Sinking in a little. No problem. We're getting there. So do people need more time for the second graph, or can we keep going? Hands up if you need more time on the second one. Okay, I'll assume that 10 of you probably are lying, so we'll pause. Okay, so in this case, we normally have a period of 2 pi, but 2 pi divided by 1/3, that's 6 pi now for the period of this graph. So 6 pi is how long an entire cycle is. That means my key points are going to be every quarter, so 3 pi over 2. Okay, so just to show you what that looks like, here's 3 pi over 2. Here's the next key point, and then I wouldn't have enough space, would I? No, I wouldn't have enough space for the next one. This side, I go backwards then. I'll have a key point there, and I'll have a key point there. Okay, so here's my key points. It's a sine graph. I'm going to go from the middle to the top, to the middle, and I don't have, it's going to go off on my graph here, so I'll go backwards this time. Now I go from the middle, it'll be down to the bottom, and then it'll be back to the middle. So this is as much as I can fit on the graph that I've been given. But it's quite a bit wider, right? Because its horizontal stretch factor is 3. It's triple the width, so that's why it's blown out so far. Okay? But if you're not already thinking this way, you have to start thinking about where your key points are going to line up on the graph. If you know how long the new graph is, divide it by 4, you'll know where the key points are going to be in the new graph. So you're going to put them together for me now. Give them a try. Amplitude and period have been changed on these graphs. Transform them. Okay, so for the first graph, we are going to move up with an amplitude of 3/2. And the key points and the period on this, it's going to be 2 pi over 2. So this is my new period, which means I have key points every pi over 4. So here's where I start, and that's pi over 4, pi over 4, pi over 4. Those are where my key points are going to be. So the first one, I'll go up to the top, which is at 3/2. Right now I go up by that much, back to the middle, 3/2, back to the middle. So that's what the graph could look like for 3/2 sine 2x if you use the same scale I have. In the next one, the amplitude this time is 1/2, and the period is going to be 2 pi normally, divided by 1/4 is 8 pi, or you can think of it as times by 4, which is the horizontal stretch factor. So my key points are going to be every 2 pi. Okay. So here's where my key points are going to be. And I'll go backwards on this graph too. So cosine, normally it starts at the maximum. This time the maximum is going to be a half. Then I go down to the middle. Then I go down to the bottom, which will be negative a half this time. If I repeat that process, I'm going to have this, well, kind of this graph. Try it again. Not bad. Not good, not bad, but anyways, that's the cosine for 1/2 cosine 1/4 x. Can I see, how many people got at least one of those graphs? Excellent, okay. So we're going to leave cosine and sine behind for a minute, and we are going to take a look then at tangent. So tangent is very specific about what you need to know, so we're going to just start with the graph. So I am going to change my window. Oops. Just move this over for a sec. So it matches the one, oops. There, okay. So then I'll put in the tangent of x graph so we can see what it looks like. Now, what I'm going to, has anybody heard of an asymptote before? Asymptote? Yeah, okay. So there are asymptotes on this graph. I'll show you what they look like. There's one at negative pi over 2. And it looks like that. And then there's another one. In fact, there's many asymptotes on this graph. But that's one of the key things we're going to need to know about. So I'm going to try and transfer my picture onto this graph. And I'll start with those asymptotes. So the asymptotes that we had were at negative pi over 2, pi over 2. And they would actually happen again right here. If we kept going. And the tangent graph itself, there's a few key points that we're going to put onto it. So the first one that's easy to find is right here. It's where it crosses the axes, where its x-intercept is. And then the next one's not quite as obvious, but right here you can see it's equal at pi over 4, it's equal to 1. You guys would remember this from your special triangle, right? 45 degrees and 1 and negative 1. So those are the ones I'm going to use to kind of guide me through it. It's this point here, and this point here. And it hugs this asymptote and goes to the other side. Same thing, if I repeat that pattern, it's going to be those 3 key points. Starts on this side of the asymptote, goes across. And like that. Okay. So, can you see that this is a periodic graph? That the shape is being repeated? What do you think the period of the graph would be then? Yeah, in this case, if you look at one tangent cycle, that distance is pi. So the period of the graph would be pi. Be careful because that's different, right? Sine and cosine are 2 pi. This one's different. It repeats every pi units. Okay. The asymptotes are going to be at negative 3 pi over 2, negative pi over 2. This pattern keeps going. And we'll talk about why those values come up. But can somebody, what do you think the next asymptote's going to be if I want the next positive one? 5 pi over 2 is right? Yeah. And what if I want the next negative one? Negative 5 pi over 2, yeah. So the domain for tangent is going to be everywhere but asymptotes. Oops. So that means the domain is everything but x cannot be. Pi over 2 plus any multiple of pi. That's the pattern that you're looking at, where n is an integer. And the range for this graph is all real numbers. It's not bound. There's no amplitude. We don't talk about an amplitude for this graph because it goes through all real numbers. And then the key points that I had mentioned there, that was the points at 0 and 0. And then it was at negative pi over 2, negative 1, and pi over 2, 1. And then your x-coordinates, you can just add just pi n, and you'll end up at the next key point. So for example, if you just remember those three, and if I wanted, where does this one show up the next time? Well, go pi units backwards, and you'll end up at that point. Go pi units backwards. So you follow the same pattern, it's just that you're moving the graph over by pi each time. That's the period of the graph. Okay. So aside from this basic shape of the tangent graph, that's one thing you need to be familiar with. The other thing is why these asymptotes come out where they do, and it connects nicely with the unit that we just worked on. Can anybody think of why there's an asymptote there? This is a spot where the graph like explodes. It's not allowed to touch those asymptotes, and it gets very, very big and very, very negative on either side. Yeah?
On the unit circle, there are certain points where you have to divide by 0.
That's right. That's right. Excellent. So if you couldn't hear Tony, he was saying that on the unit circle, there's certain parts where you'll divide by 0, right? Because you had one thing we already talked about was tangent of an angle was y over x. So when x equals 0, you get these asymptotes. Can we be more specific about that? It's not just the fact that x equals 0, but what else? What's another way of describing x equals 0 on the unit circle? Yeah, that's right. The cosine of that angle would be 0 because the tangent of the angle is the sine over the cosine. So that's another way you can find the asymptotes. Tangent is sine divided by cosine. So if cosine equals 0, you're going to have an asymptote. Now you could solve a trig equation, which is what we were just doing. So it should be something familiar if you forget how to draw the graph. Okay, so aside from that, we're gonna stop with those basic forms and basic shapes. Here's some practice for you to get started on today.